But anyway, homework 3 is out. It's been out since Monday, but I didn't talk about it at all on Monday. I just want to talk about it briefly here. The whole theme of the homework is WebSockets. Objective 1, we learned how to do on Monday. You know everything you need to know for Objective 1. You have everything, all the knowledge you need for that. Objective 1, check, we're done. I'm done in lecture at least. We have Friday for demos, if you saw that on the schedule, WebSocket demos, so I'll go in more depth on it. Actually, I don't know what else I have to say about Handshake, but I'll give demos at least and show you what it's all about. But you have everything you need to know to build that. Now we want to start sending messages over that WebSocket connection. Objective 2 is just getting pretty much any messages to work. Objective 3 is adding features to that, handling different situations, different scenarios. Objective 4 is adding a database to that. And all 3 of those objectives we'll be able to do by the end of today. You'll have everything you need to know to do up through Objective 4. And then Objective 5, this will take us a week to cover. Objective 5 is, it's obviously not a bonus objective, but I kind of look at it as that. Like the bulk of your work is going to be implementing WebSockets, and then WebRTC is going to be an application of that WebSocket that's going to be, I think, a fun application of it. And to be honest, Objective 5 isn't that hard, but it takes a lot of lecture time to talk about the background of it. Whereas WebSockets are kind of the opposite. I don't need much lecture time to tell you how to do WebSockets, but it's going to take you a long time to implement. WebRTC, I got a lot to talk about with WebRTC, but when you go to code it, the way I have it set up at least, you don't have to do much for Objective 5. But anyway, we're going to learn how to do through Objective 4. Objective 4 itself is just adding a database to it. We already know how to do Objective 4, but I'm going to show you how to do Objectives 2 and 3 at this time, in this lecture. So I know a lot of you are probably still working on homework 2 anyway, but if you're ready, you're on homework 3, you're ready to start it. There's nothing holding you back in terms of knowledge. You're ready to go into it after today's lecture. So let's talk about it. WebSocket frames. This is that scary protocol, that formatting that I showed you last time. I shouldn't say scary, but we're going to learn all about this. This whole thing, we're going to understand the whole thing by the end of today's lecture. Oh, I don't really have anything on that slide. So we made a connection. We got a WebSocket connection. We did that handshake. We computed the accept based on that key. We used SHA-1 and base64 encoding. We computed that. We got a connection. We're keeping the TCP socket alive. And when we keep that alive, by the way, in your code, I'll have demos on Friday and show you this. But when we're in the code, we don't want to close that TCP connection, because that TCP connection is now a WebSocket connection. In Python, this means not hitting the end of your handle method. You hit the end of that handle method, the TCP connection is closed. So once a connection is a WebSocket connection, you don't want to get to the end of that method. You got to have some control flow, control structure, i.e. a loop, that's going to continuously read these WebSocket frames and handle them, send WebSocket frames to other users, and add any of the features that a WebSocket connection should have, and then just continuously do that. Okay, let's talk about protocols for a second. I don't talk about this too much, and this is kind of where it fits the network stack. I'll mention a little bit here. So protocols are just a way to define the order of, it's a little too broad, but protocols are a way to agree on how we're going to communicate, and some protocols are defining the order of bits as they arrive over the internet. So when we send bits over the internet, it's all just ones and zeros, that's it. And then the routers of the internet have to make sense of these ones and zeros. So we have protocols to make sense of the ones and zeros that are being sent. We saw IP and TCP. I showed these, I didn't explain them, and I'm not really going to explain them much today either. That's for modern networking concepts. But we have these diagrams, is it fair to call these figures? But this is specifying what each bit means. So when an IP packet is sent over the internet, this is going to be the first bit that's received. The first 1 or 0, the second 1 or 0, the third 1 or 0, the fourth 1 or 0. And the router knows to take those first 4 1s and 0s, those first 4 bits or that first half a byte, and know that that represents the HTTP, or the IP version that's being used. And for current day, for today, that's either IP4 or IP6, IPv4 or IPv6. And then this is an IPv4. If it's a v4 packet, it's going to be the rest of the bits in this order. So when the bits arrive in this exact order with this structure, we can make meaning of those bits based on their position. So the bits in specific positions have specific meaning. We saw the same thing for TCP. We're going to have the first 2 bytes are going to be the source port, second 2 bytes are going to be the destination port, sequence numbers, etc., based on the position of the bits. I get a bunch of 1s and 0s over the internet, and I treat them in order. I know where a packet starts because it's the bit after the previous packet ended, and then I know that that's going to have specific meaning according to the protocol, because whoever sent this packet is going to be looking at the same, whoever coded the software that sent the packet, I should say, looked at the same documentation as I am. They did things the same way according to the protocol that I am, and then I can parse that code appropriately. Same thing with HTTP. We get away from the bit level at HTTP, but it's still a way to communicate. Send your bytes to represent these things. The bytes /r/n have special meaning and things like this. The browser and your server both speak the same protocol based on the same documentation, the same RFC. That way we can effectively communicate. So now we want to go through this one. This is the first one that we do have to parse and assemble. WebSocket frames. This is the same thing as the TCP and IP. It's specifying which bit, based on its position, means what. And we're going to parse those bits to extract the right information that we need. So when a packet is sent over the internet that contains a WebSocket frame, it's actually going to look like this. And the position of the bits is going to be very important and have to match the protocols. The routers of the internet are going to read the IP headers. They're going to read all these bits, and then by the time it gets to a machine, IP's job is to get this packet to a specific device on the internet. That machine is going to ignore the IP headers and read the TCP headers to figure out which process to send this information to and how to reassemble the packets, how to get that information all together. And then once it's all reassembled, it's going to send its payload, which for our purposes now will be WebSocket frames. It's going to send the bytes for the WebSocket frame to our specific process, so we can read that information off the TCP buffer. So by the time we get it, the first 2 layers are peeled off, the IP and TCP layers, and we're going to start reading at the WebSocket protocol. Whereas with an HTTP request, we wouldn't have the WebSocket protocol here. We had the HTTP protocol, which didn't work at the bit level. It worked at more of a string parsing level. It just sent a bunch of bytes and said, here's how you make sense of the bytes. There's headers, there's /r/n's, all this stuff that we've been dealing with so far. Now we're heading down to the bit level. I don't know about you, but I get excited about it. I might be alone in that, but I get excited. We're going to start seeing some bit level parsing. Which, the reason I get excited about it is because we talk about bits and logic and things like that in computer science a lot. When you took 191 at the very least, you saw quite a bit of bit level stuff. But it usually doesn't matter. It's cool, it's fun to know, I guess, but it doesn't really matter. Here's a case where it actually matters. You actually have to take that stuff that you learned and actually throw it in your code to make your code do the right thing. So I get excited in that sense. It lets me have a practical application for something that I used to not have a practical application for. Yeah, bits, baby. Yeah, you need to do masking, but a little more than that as well. Oh, I didn't even read this slide. All right, so we want to read things at the bit level. So we're going to get our stream of bytes. You're reading from the TCP socket just like you did before, except now instead of text and images coming over that stream, it's going to be bytes in this format. You're going to get this 1 byte at a time, or not 1 byte at a time, but you're going to read from the TCP stream and get, a chunk of bytes, and we have to follow this protocol to make sense of those bytes. So no matter what language you're using, you're going to have a byte array that you read from the TCP socket, and then we can read those bytes according to this protocol. So for example, if we access the first byte of that array, if we say, hey array, give me your value at index 0, and it's a WebSocket frame, we already did the WebSocket handshake and all that stuff, that byte is going to contain the first 8 bits here. It's going to contain this fin bit, our 3 reserve bits, and our 4-bit opcode. All of that will be in the first byte of that data. If you say, hey, give me the value, give me the byte at index 1, you're going to get the next 8 bits, this mask and payload length. So we want to make sense of this stuff. We already get this in 8-bit chunks, and we want to parse those apart to look at their individual bits. Yeah.
What do you mean that bytes are represented as 8-bit integer values?
Like,
you mean like the individual bytes have 8 bits in them?
yeah.
I thought you were talking about like the way to about
Like if you print out a byte, you usually get, I guess it does vary by language what you actually get if you print it out. But a byte is usually represented as an 8-bit. Like you have an int. All this is language dependent, but ints can be like 32-bit or 64-bit integer values. A byte is typically just an 8-bit integer value, unsigned. So it's going to go from 0 to 255 and then wrap around if you add 1 to it back to 0. My point of this bullet point is you can treat them like numbers. If you have a byte and you treat it like it's an int, you usually, I think, I don't want to say every language, but like most languages, that's how it's represented, and you can just do math to it, which is going to come in handy. But one thing that we don't often care about with our integer values is that they are binary. Every integer is a binary value. If you've got a 32-bit integer, it's literally 32 ones and zeros. That is what it is. Now, modern languages, compilers, interpreters, like everything, by the time it gets printed to the screen, all those things are going to work together to say, hey, look, our human wants to read this value. Maybe let's not show them the ones and zeros. Like maybe let's actually show them the decimal number that they're used to seeing. But they are ones and zeros. We just have not a facade. We just have this illusion that they are decimal numbers. But there's no decimal numbers in a computer. They are all binary. So we can take advantage of that fact and start using our bitwise operators on these integer values. So if we have these first 8 bits as an integer value from 0 to 255, we could do something and say we want to read this opcode. What we can do is mask out, what we call mask out the bits that we're interested in, or mask out the bits that we're not interested in, I suppose, using a logical AND operator. So if I take this first byte from my stream and logical AND it, which is a single ampersand in any language I've seen. This is why, if you ever wonder why we use 2 ampersands for a Boolean AND, it's because single ampersands are already used for a logical, a bitwise AND. So if we AND it with 15, which is 1111, it's going to zero out the 4 most significant bits, and it's going to return the opcode as a value between 0 and 15.
That basically disregards thin and the 3 reserved ones?
Correct.
It says, oh, if 4, 5, 6, or 7, if either of those are 1s, then it will stay at 1 in that code.
Yep. Yeah, so no matter what I have for this byte, whatever and 0, whatever and 0, 1 and 0, all these will be 0 because it's an AND operator. but the 4 least significant bits will be whatever the 4 bits are for the opcode. Whatever these values are, if it's a 0, 0 and 1 is 0. If it's a 1, 1 and 1 is going to be 1. So it's going to perform a bitwise AND operation.
And the whole frame is sent by bytes?
Bytes, yeah. So you're reading the frame exactly the way you read your HTTP request. You're just going to the socket and calling receive, or in JavaScript, your callback is being called. Yeah.
Is the mask, for this example, to get the operation, code will always be a bit mask of 15, or is this what we read from?
It'll always be a bitmask of 15. Like this opcode is always going to be bits 4 through 7, or the 4 least significant bits of the first byte. So to extract those 4 bits, it would be 15 because 15 is 00001111. So if you're interested in the 4 least significant bits, 15 is your number. Yeah.
I don't understand this chart. But you said it's the byte at index 0, but the chart makes it seem like it's the index 4, 6, 5, 6.
But a byte, 8 bits. So the first byte is 0 through 7.
Okay.
Right? And that's important, I hope. Because it takes a while to start seeing what this chart is saying. So it's a very important thing, if anybody has questions on that. The first byte is 0 through 7 here. The second byte is going to be your 8 through 16, 8 through 15 on this chart. And so on and so forth. So this chart is 4 bytes wide. So 4 bytes will give you an entire row of this chart. Yeah.
I think I'm confused because the number of the byte number doesn't actually line up with the bit number.
Sure. Yeah, these are all bit numbers.
With the byte number, like for the first byte, it should be over 8, but it's over like the 0 right there.
Yeah, because it starts at 0, so it'll be 0 through 7. It'll be your first 8 bits. And then this one, this is 10, 11, 12, 13, if anyone can't see that one. Yeah. And then it goes up to 31, 0 through 31 for 4 bytes.
So 0 through 7 is the first byte, and what's 8 and 9?
That's the start of the second byte. So 8 and 9 would be the first 2 bits of the second byte.
Doesn't the second byte start from 1 and 0, 0?
Mm-mm. Bytes are 8 bits. So we have 32-bit wide here, so we have 4 bytes. So byte 1 is going to be your 0 through 7, and then your 8, 9, 10, 11, 12, 13, 14, 15, those are your next 8 bits, so that's your second byte. Bits 16, 17, 18, 19, 20, 21, 22, 23 are going to be your third byte, or the byte at index 2, and then the rest is going to be the fourth byte, which will be the byte at index 3. Yeah.
I think I realized that. I thought those numbers at the top were the byte numbers, but those are actually
The bit numbers, yeah.
the next, like the tech place.
Yes. Yeah, these are the tens places, and then these are the ones places. Yeah.
Does the array of bits continue until the payload data is finished sending, or only 6 rows of 32 bits?
Until the payload is gone. So there could be 1,000 lines here. Ooh, a colored version. I should use that in my slides. Okay. Any other questions about how to read this thing? How to even look at it? Yeah. You read across first and then down. Yeah. Yeah, so where it says extended payload length continued, like that would be the second row. So the first byte in that row would be byte 5, or the byte at index 4. Yep. Yeah, we have 4 bytes wide and then a bunch of columns. Mm-hmm. Yeah. Yeah, bless you. The third and fourth, if the extended payload length exists. So I got to get into, before, like the first 2 bytes are fixed, those are what they are. After that, things get Bless you. Things get more complicated. It's like the rest of lecture. Payload length is complicated. That'll be a lot of the work for your homework. It's getting that payload length. But yes, I'll give you a soft yes on that, but we're going to complicate things. All right, so let's talk about what these bits represent. Bit number 1, fin. This is the finish bit. If this is a 1, it's the last frame of your message. For objectives, I guess just objective 2. You don't handle frames in objective 1. But for objective 2, this is always going to be 1. Because the frame that you're reading is going to be the last frame because it's the only frame. For objective 3, this might be a 0. If this is a 0, it means that there will be more frames. This is not the last frame of this message. So you can have multiple frames containing a single message that you then have to parse them all and then concatenate the data together to be able to get the entire message. So if this is 0, you know at least one more frame is coming. And if you get 5 frames with zeros for the fin bit all in a row, and then finally you get one with a fin bit of 1, you know those 6 frames all contain the same message, and you have to jam them all together to be able to get the entire message, all the payloads together to get the entire message. So the fin bit, is this the last frame of this message? Reserve bits. These are reserved for if you have any extensions to the protocol. We're not going to mess with this. I shouldn't say anything, but I'm not sure of these being used anywhere. I'm sure somebody does, but we're going to assume these are 0, 0, 0 for your homework, which will always be true. Your browser's always going to send all zeros for these reserve bits, so we save some time there. We're not going to mess with these things at all. Opcode, your operation code. This is metadata about the content that's being sent and what some of the meaning is. For example, if it's 0001 for the opcode, that means this is text data. You can safely parse it as UTF-8. If it's 0010 or 2, it's going to be binary data, meaning you cannot parse it as UTF-8 and you need to treat it as raw binary. So if you're sending an image over WebSockets, you would send an opcode of 2 or 0010. And if you're sending text, 0001, 1000 or 8, oh, I bit my tongue, is going to be a closed connection. That's a request to close the WebSocket connection. If you get that opcode, it's time to exit your loop, exit that handle method, and you're done with that connection. Or 0000 for a continuation frame, and the opcode should be the same as the first frame that you received. So if the first frame was 0001 for text, your continuation frames are all going to be text. It wouldn't make sense for the opcode to change. So we do 0000 for a continuation frame. The mask bit, it's a 1 if a mask is being used, the 0 if a mask isn't being used. I have a lot more to say about masks later on, but I'll keep it at that. I guess I won't. This will be a 1 when you're receiving messages from the client and a 0 when you're sending frames back to the client. That's all I'll say about masks until we get there, until we get to this masking key. Oh my goodness.
So it's 1 if it's on and 0 if it's off?
Yeah. I still didn't advance the frame. What am I doing here? And then payload length, similar to content length. We want to know how many bytes are in the payload of this frame. This is where probably the bulk of your work is going to be when you're coding this up, at least for objective 3. So the payload length is going to tell you how many bytes are in the payload of the frame. This is going to tell us how many bytes we need to read. So when we're sending giant frames, it'll tell you how many bytes you need to read so you can enter your buffering state just like you did with content length and figure out when to stop buffering and actually process the message. So you're going to have that. For content length, you'll read that to figure out how long to buffer. And you're also going to want to read that to know where the end of the message is. Sometimes you'll get 2 WebSocket frames being sent back to back. If the client is sending 2 frames like almost simultaneously, you'll need to be able to parse that apart and know when to stop reading one frame and when you're starting to read the headers of the next frame. So payload length, very, very important. And as a bonus, it's kind of complex. It's not super complex in the slides, I'll tell you that. It's not too crazy in the slides, but when you go to code this, it gets tricky. Like it's a good programming challenge. So the payload length can be represented as either 7, 16, or 64 bits. So we have different ways to be able to represent the payload length. And I should mention, WebSockets are designed for optimal performance, minimal overhead. It's really a thing of beauty, I think. But we have 2 bytes that are always being used. If we have a mask, we have another 4 bytes here. And that's it. Like, that's the overhead. Several bytes. 6 bytes minimum if you're masking, and 2 bytes minimum if you're not masking to be able to send a WebSocket frame. Very, very minimal overhead. Think about this in comparison to HTTP. By 6 bytes, we can't even type HTTP/1.1. We can't even get that in 6 bytes. So the amount of overhead in HTTP with all these headers and everything, the new line characters and all that, there's a lot of overhead compared to WebSockets. WebSockets are lean, they're very efficient, very optimal, a very efficient way to communicate over the internet. Once a WebSocket connection is made, sending messages back and forth, most of what you're sending is your actual message itself. Very elegant, very cool, very nice protocol. That's why I think WebSockets are here to stay. I don't see these being replaced. It's basically just TCP with almost no overhead. It's a beautiful thing. Yeah.
Is the next bit after the length, rather than mask or payload? Does that mean it would be the payload after the length?
Well, let's get there. We'll get there. There's a lot of if this, depending. This next bit could be 3 different things, depending on the situation. So I got a bit to explain with that one. So the payload length is going to be these 7 bits if the payload length is less than 126. The payload length is less than 126. So let me explain this in terms of parsing. When you're parsing the payload length, you're going to extract those 7 bits and you're going to read its value. If that value is less than 126, that's the payload length. So if I got a payload length of 150, that's a bad example. If I got a payload length of 105, I'm going to read that 7 bits. Those 7 bits will tell me 105. That's my payload length. That means my payload data down here is going to be 105 bits. 105 bytes. Payload length is always in bytes, just like content length. I know that's the amount of content that I need to read. And then then none of this would exist. And the next bit in that case would be the masking key. There would be none of this other stuff. If the payload length is between 126 inclusive and 65,536 exclusive, which is 2 to the 16, if it's in this range where it can't be represented with 7 bits, but it can be represented in 16 bits, is where those numbers come from, then the payload length, the 7-bit payload length, will be exactly 126. And then the next 16 bits or 2 bytes will be your actual payload length. So if this number is exactly 126, then the next 16 bits will be your actual payload length. So if you see a 126 there or a 127 that we'll talk about, that means that number is not representing your actual payload length. It means you need to do some more parsing and more reading of this protocol, bless you, to be able to figure out the actual payload length. So if this is 126, your next 16 bits is your actual payload length that you need to read. And in that case, the masking key would start right here. If you have payload more than, I almost said 16K, more than 64K, or 2 to the 16. If your payload length is greater than that, greater than 2 to the 16 minus 1 to be technical, it's inclusive, then this payload length, the 7-bit payload length, will be 127 exactly. It'll be 127, and then the next 64 bits all the way through here. 64 bits to represent your payload length. 8 whole bytes to represent your payload length, which means the max payload length for a WebSocket frame would be 2 to the 64 minus 1, which is a ridiculous number, which is about 16, which is exactly 16 exabytes, which is about 16 million, no, I keep saying about, it's 16 million terabytes. No, I think that one is about. 16 million terabytes. That's how big a frame can be. I think whoever, the team who was designing this, probably looked at IPv4 and said, we don't want to run into that issue. We're going to future-proof the hell out of this. And they went up to the exabyte level. So a WebSocket frame, and even if you do exceed that, you're just going to use the continuation frames and a fin bit of 0. You can communicate as much information as you want over these things. Yeah.
I think that's like this more than like the sum total of all the chat traffic in human history or something.
Probably, yeah. It's a big number. That's a lot. Oh, maybe not. I don't know. Terabyte's not that much anymore. 16 million of those? I don't know. It's a lot, though. It's more than you're going to need. Yeah.
So tell me if this is right, because it's kind of contradictory, but not really. If the length is 125 bytes, the 7-byte area, or the 7-bit area, will say 125, and then immediately after, we're going to be on the master key
Yep.
data. If it's 126, the payload length, the 7 is going to be 126, and then the extended payload length is also 126?
The extended payload length, that 16 bits, will be your actual payload length. That would, like if I'm sending a message that's 2,000 bytes long, this payload length, the 7-bit, is going to be a 126, and then this 16-bit value would be, did I say 2,000? Would be 2,000 in binary.
Okay. So it would be 126 for both, if the actual length was 126?
Yes. Oh, if it was, I didn't hear that part. If the length is actually 126, yeah, 126, and then we use 2 bytes for 126. Yeah.
The library compass is 10 terabytes.
Okay. Yeah.
And then if it's 100,000 bytes, the payload length would be 127. The extended payload length continued would be 100,000, but what is the extended payload length?
It would, if it were 100,000, if your payload length is 100,000, this is 127, and then these 8 bytes, which will be mostly zeros, will be the value 100,000 in binary, which will take up, some of these bits over here and these bits here. But most of this will be zeros because 64 bits it's a lot of bits to represent payload length. But if you have a number that can't fit in 16 bits, you got to use 64 bits.
You got to use the whole 3 rows, half of the bottom row, half of the top row. Whole
There's only 3 options here. Either your payload length can fit in 7 bits, or you need 16 bits to represent your payload length, or you need 64 bits to represent your payload length. So if you can't fit in 16 bits, you got to use 64 bits.
And it knows to read the whole thing if the payload length is 127.
You know to read the whole thing if the payload length is 127. You're going to code it that way. And the browser is going to code it that way. The browser developers are going to code it that way, because that's what the protocol tells us to do. The protocol doesn't do anything. It just tells us humans how to write code. So we're going to code it according to the protocol. That's payload length. It's pretty complicated. It's not too hard to understand in the slides, but I think you can all see that when you go to code that, it's going to be some work. So let's move on to masking. If this mask bit is 1, a mask is used. If the mask bit is 0, a mask is not used. If the mask bit is 0, these 4 bytes, 4 bytes don't exist. And right after the payload, whether it's 7, 16, or 64 bits, the next bit is going to be the start of your payload. If the masking bit is 1, then you're going to have 4 bytes right after your payload. Again, whether it's 7, 16, or 64 bits. Right after the payload, your next 4 bytes, if the masking bit is 1, is going to be 4 bytes of a masking key. These 4 bytes are random. The client is going to randomly generate a 4-byte masking key for every message that it sends. You're going to have to read this key and then XOR each byte of the payload with the appropriate byte from that key. I feel like I worded that one weird, but you'll see in the example. So when the client gets the payload, they got a payload, they're ready to send this message. They're going to take every 4 bytes of that payload and XOR it with that masking key. And when they get to the end, if the payload length is not a multiple of 4, they're going to take however many bytes they need to be able to mask the rest of the message. So the entire message is masked using this masking key using XORs. When you're reading a message that's been masked, you're going to read the masking key and then XOR it with each 4 bytes of the message. So for example, I read the first 4 bytes of my payload, and I get, the user, the client is trying to send this message. They want these 4 bytes that they're going to send to your server. They generate a random mask of this. What they're going to do is XOR this mask and the first 4 bytes of the payload that they want to send. So they're going to XOR. This XOR is usually the caret in most languages. If you haven't used it yet, if you're not familiar with XOR in coding, I know you are from 191, but in coding, they're going to XOR 0 and 0 is 0, 1 and 1 is 0, 0 and 1 is 1. XOR operation bitwise. That's what we're doing here. So we get this message XOR'd with the mask, and then when you read this message again, you're going to XOR it with the mask again. So if we XOR this with the mask again, 0, 1, 0, we XOR it again bitwise, what we end up with is the same exact message. So, so we're taking a message and XORing it with the key twice, and this is a commutative operation, XOR is. So if you take something and XOR it with itself, you get straight zeros. So it's like XORing with straight zeros, which is going to give us the original message back. So we get the message XORed twice, but when it's sent over the internet, it's going to be just a mumbled mess of crap. Where's my slide that says why? You should all be wondering why we mess with this. I should have a slide that says that. I think I do on Monday's lecture. Maybe I just thought, well, I said it on Monday. The reason for this, it's not security. Please don't think that it's for security, because everybody who has access to these bits has access to the masking key as well. Everybody can unmask this. So it has nothing to do with security. Don't ever think about that. Think that this has anything to do with security. This is just like the key being random in the handshake. This is a cache buster. This is to make sure that the same message, say I'm in chat and I just say the same dumb thing, I'm just spamming something constantly over and over and over again. I don't want every message to look the same over the wire, because then I might have an aggressive cacher that's going to say, hey, last time you sent this, the server responded with this, I'm just going to respond with this again. Maybe in that example, that's what we would want. Maybe we want to stop that behavior. But if you send the same message over and over, we don't want to get cached. So this mask is going to make sure every frame looks very different, even if it's the same message, so we can get not cached. We're not going to get cached on these. Yeah.
Which side comes up with the mask?
The client.
And it's unique to that client or that frame?
That frame. So you're going to XOR the payload with the masking key, and that gives you your message back. Then you finally can have the message and process that and do whatever you're doing with that. I recommend in your code to do this 1 byte at a time. Iterate over your payload. Find out which byte of the key you should XOR that byte of the payload with, and then XOR it. If you do it that way, 1 byte at a time, instead of trying to do it in 4-byte chunks, it'll reduce the amount of index out of bounds errors that you see while you're debugging. Bless you. When you send a frame, you're going to use the same exact format, the same exact protocol, I should say, in the same format of this. I guess format's true too. The difference is your mask bit will be 0, and you will not use a masking key. Other than that, it's all the same thing. So when a client sends you a message, they mask it, they want to bust cache and all that stuff. When we're a server sending something to the client, we're not getting cached. Like, that's not how caching works. The server doesn't get cached. So we don't have to worry about that. We're just going to send it without a mask. No problem. So your mask bit will be 0. You'll have to compute your payload length, and we will test with messages where your payload length will change. But we will send, let me just give an example because I don't know how to word that. Say the client, we're going to send a message, we're going to be the client while we're testing. We'll send a message of length, say 125 to your server, and then you have to escape HTML, which is going to increase the length of that string. And then that's going to push it, we're going to put some HTML in there, which will push it over that 125 boundary, and then you'll have to compute the extended payload length for 16 bits. So we will test with that. I'll give you a heads up right now. We will test for that. So your payload length format might change from the frame you receive. We do that because students like to just steal the headers from the client frame and then just cut and paste those into their frame and not actually build frames. So we're going to make sure the payload length changes the number of bytes needed when you escape your HTML. So heads up on that, you have to actually compute your payload lengths. It'll just steal it from the client because you have to escape HTML. Assumptions for the homework: reserved bits are always going to be 0. Opcode will be one of these 3 cases: 1 for text, 8 for close, or 0 for continuation frame. You're going to see one of those 3. So if it's anything other than that, I don't care what your code does. It can just explode or whatever. It's fine. If you see anything other than those 3 opcodes. And those are all the assumptions. I just said that. Yeah, we're good. Any questions? Yes?
So, like, if your payload is not multiple of 4, like, let's say you have a remainder of 1, do you use the most significant or the least significant?
Most significant.
Okay.
Yeah, good question. So the masking key, like this byte of the masking key will be XORed with this byte of the payload, this byte with this byte, etc. This byte with this byte. So you start with this first byte, the most significant, as your first thing that you're going to XOR. And then when you get to like the 5th one, that will wrap around back to the first byte of the masking key. So if this only had 5 bytes, for example, this 5th bit would be XORed with this first, 5th byte would be masked with the first byte of the masking key. Near star.collapse. Yes. If your code works, I would be massively impressed. Yeah. Yeah, so you're reading from the TCP socket just like you did for HTTP. So you get that byte array in that same exact way, but you're going to use this protocol instead of HTTP. It's however you want to code it. You don't necessarily have to slice it. Probably at some point you will, but however you can code up this protocol, that's what you got to do. I hate that every clock's different. I'm looking at 3 different times here, all provided to me by the room, in which case I'll use my phone. 3:47. Any other questions? I think 3:47 is a good stopping point, so let's do it. Have a great day. I'll see you everybody Friday.